Okay, we're going to look at some trigonometric inverses now. So a trigonometric inverse obviously is just our cos inverse, our sine inverse, our tan inverse. They appear this way in your log tables, so that's the kind of version that you need to be the most used to, I suppose. So it appears with kind of x over a, and in our log tables, a is always for a constant term. So a is always a number. So a is always a number. The x part then could just be x itself, but it could also be an expression. It could be any sort of kind of expression part, I suppose, really could be slotted in there over a constant. And the way we're going to approach these, and I suppose we decided that we would just approach them all in the same vein and in the same way, was to make a substitution. And that's what I'm writing over here. So our substitution is going to be, we're going to use z for our angle. So whatever the angle is, we're just going to put in z. And by doing that, we're going to end up with z over 1. So our a will be 1, and our angle part at the top will be like the expression in the question. Okay, so our angle is 1, and we have our expression there. And that's just going to enable us then to solve these questions in, I suppose, a somewhat easier way. Hopefully, I suppose that's the ideal scenario that we have. We may have situations where we could use the way that it is in the log tables, and I will show you maybe both versions, but if you're kind of iffy on it, it might be best to just say we'll always substitute in. It does require maybe a tad more algebra work, but if we kind of get used to the steps required and the way that we approach the questions, then we should be okay with them. But otherwise, we can see the rules that are there. They're there in the log tables. We just follow them the same way as we would any other rules. So looking first of all at these two examples. So first of all, we have tan inverse of 2x. So I'm going to make my substitution. I'm going to say that z is 2x. And I'm going to take this as being tan inverse. So let me get my y then. So my y is tan inverse of z over 1. Okay. So dy dz then, looking back up at my rule, is going to be 1 over 1 squared plus z squared. I'll fill that in red there just to really remind us to sub that back in. Z squared, and dz dx then is just going to be 2. Okay, so lastly then, to get dy dx, we just need to bring those together. So 1 over 1 plus z squared, which was 2x all squared, multiplied by 2. And I get 2 over 1 plus 4x squared. Okay, that was my answer there for the first part. For the second part, we see maybe a more kind of typical example where the substitution will serve us well. So again, we will say that z is x cubed plus 3, which means I can rewrite my initial question here as cos inverse of z over 1. And I have my z obviously already established here as x cubed plus 3. I can get the derivatives of each of these, so dy dz. So we're using a chain rule here. So dy dz is minus 1 over square root of 1 squared minus z squared. And then dz dx is going to be 3x squared. Okay, so bringing all this together then to give me dy dx, I'm multiplying both of these. So minus 1 over the square root of 1 minus x cubed plus 3 squared multiplied by 3x squared. And we're just going to bring that all together then to give us my answer. So square root of 1 minus x cubed plus 3 squared. And we're going to leave it in that form there because multiplying that bracket out is not going to leave us with anything simpler. Okay, that is actually the nicest format that we could leave our question in. So we can see how our substitutions there can save us a little bit of time. We're going to see with the next question now the difference between me making kind of my substitution and me using it in the format that I have it here. So it's kind of a full substitution versus, if you like, a half substitution. So let's take it to the side here. If I make a full substitution, so say say that z is everything that's in the angle 2x over 3. And I'm going to say then that y is just sine inverse of z, which means dy dz is going to be 1 over the square root of 1 squared minus z squared, and dz dx is going to be 2 over 3. okay, 2/3, because that's the same as me writing 2/3 x. Okay, so following on here, we're going to have to substitute back in our answer for z, and in this case we said z was 2x over 3. And we're going to be multiplying this by my derivative, which is 2/3 here. So 1 over square root of 1 minus 4x squared over 9. Okay, 4x squared over 9. Oops, sorry. 4x squared over 9 multiplied by 2 over 3. So continuing to simplify this down here, then I can get a 2 on the top, multiplying top by top, 3 at the bottom, and I'm going to rearrange that bottom part into one fraction. So I'm going to rewrite 1 as 9 over 9, and that's going to allow me to bring them together as one fraction to give me 9 minus 4x squared all over 9. Okay, from my surd rules then, if we remember our surd rules, I can rewrite this then, keeping my 3 on the front, I can rewrite it as the square root of 9 minus 4x squared over the square root of 9, which of course is just 3. So I have 3 root 9 minus 4x squared over 3, which gives me an answer of 2 over 9 minus 4x squared. That's my answer here. Okay, so it does end up seeming a tad long-winded, if you like. The other version that we have is to maybe make a little bit of a smaller substitution. So instead of substituting for the entire question, we could just substitute for the top part. Okay, so y would be z over 3, which means that dy dz, we're going to use 3 instead of a. So looking back at our rule here, so it's 1 over a squared, 1 over square root of 3 squared minus 2x squared, and we multiply by the derivative of z, which is just 2. Okay, and this leaves us with, I suppose, getting to our answer in a much quicker fashion. Okay, a much quicker fashion. So it really is just a case of you deciding which version you prefer. I know looking at this, it does seem like the right hand side is an easier version. You just need to remember that we substitute in for the entire expression that we have there. So I suppose when it is a fraction, we can just substitute for the top of that fraction, but otherwise we would take the whole expression. So as we'll see now, say in this next example here, so the 2013 question, if y is equal to x plus sine inverse x, prove this differential equation. So we have y, it's an expression, we've seen this before, we know that for an expression like this we do them just in turn, so dy dx, x differentiates just to 1, sine inverse of x goes to 1 over square root 1 squared minus x squared, so 1 plus 1 over root 1 minus x squared. Okay. So we also, for this one, have to find the second derivative. We have to find the second derivative. So in order to find the second derivative, I'm going to rewrite my question here as 1 plus 1 minus x squared to the power of minus a half. So the half part means it's a square root. The minus means that it was on the bottom of a fraction. But that's going to aid me then in working out the second derivative, because for the second derivative, multiply by the power, reduce the power by 1, so it becomes minus 3 over 2, so minus 3 over 2. Okay, and we need to also multiply by the derivative of the middle part, so minus 2x. So bringing all of that together gives me x times 1 minus x squared to the power of minus 3 over 2. The power of minus 3 over 2. So let's see now, does this differential expression hold? So it's 1 minus x squared times d2y dx squared, my second derivative, which is this part that we have here. Okay, so this is our second derivative that we've got here. So let's fill that in. So I'm multiplying by x times 1 minus x squared to the power of minus 3 over 2. So that's my second derivative. Minus x times my first derivative, which was this one here. So my first derivative was 1 plus 1 minus x squared to the power of 1 over 2. And we want to see, is that going to be equal to 0? Want to know, is it going to be equal to 0? So let's just quickly have a look then. So multiplying this out, if I focus on the left-hand side here, if I focus on the left-hand side first, I'm going to have x. I have two expressions here, these two parts, that are both the same base. So they're 1 minus x squared to different powers. The one on the left here is the power of 1. This one is to the power of minus 3 over 2. So adding those together just gives me 1 minus x squared to the power of just minus a half again. So I'm adding 1 to the power there. Multiplying out the right hand side, I get minus x times, and then minus x times 1 plus, or 1 minus, sorry, 1 minus x squared to the power of minus a half. Okay, 1 minus x squared to the power of minus a half. Now I've forgotten one more little part in my expression there, which is plus x. And we want to show that this is all equal to 0. So looking quickly at this, we can see that this part here and this part here will end up kind of are the opposites of each other, so they're going to kind of cancel out in a way. And the same thing goes for the minus x and the plus x. So we end up getting 0, which is of course equal to 0, naturally enough. Okay, so nice little differential equation for us there. So the same thing applies to all of these questions. It's just really applying those substitutions for our derivatives where we can. And we're going to see this now in this next question as well. So again, we're going to be applying a little substitution for our derivative here because we have a nice full expression to deal with. So let's have a look. If we call our expression z in the middle here, I can say that z is 2x minus 1, and the derivative of z is of course just 2. Taking y then and calling it sine inverse of z, I then get that dy dz is going to be 1 over the square root of 1 squared minus z squared, which is 1 over the square root of 1 minus just z squared. Okay, just evaluating the 1 squared really there. Didn't really save us an awful lot. Anyway, doesn't matter. We're going to keep going. Dy dx is going to be dy dz times dz dx. Okay, using our chain rule here, as we have been, dy dz is this one, highlighter working there, and dz dx, of course, is this one here. So let's sub those in. So I have 1 over the square root of 1 minus 2x minus 1 squared times 2. Nice and straightforward, okay? So multiplying this out, then I get 2 over the square root of 1 minus 2x minus 1 squared. So we've found dy dx. We need to calculate its value then when x is equal to a half. So we just fill in a half for x. So 2 over, let's just write it here, at x equals to a half. 2 over 1 minus 2 times a half minus 1 squared, which is going to leave me with 2 over square root of 1 minus, well, we'll have 1 minus 1 in here. So 2 over the square root of just 1, which is of course just 1, so my answer ends up just being 2. So we can see with these trigonometric derivatives, it's very easy for them to get very complicated very quickly, but by making a simple substitution there, we actually can reduce the complexity of the question down quite substantially, I suppose. But it's making sure as well, say with a question like this, where we have an angle that has a fraction and has a constant part at the end, we can make that decision to make a smaller substitution and just substitute for the x part on the top of the fraction, leaving the constant part the same, leaving it as 3. And that's, I suppose, leaves us with an easier question to sort out. It saves us working with all the algebra that we have there and kind of rearranging surds and things like that. But of course, those are things we really, I suppose, should be striving to be able to do as well. But it really is just kind of making that decision for yourself. What you're going to remember to do. If you're going to remember to just always substitute in for z, then that's fine. And I suppose in many cases where you have a complicated exponential, the bottom of the fraction does tend to just be one. It tends to just be an expression with no bottom to the fraction. If you had that, it may be simpler again to just focus on taking your substitution z for the x part of the angle then.